Okay, we're back. Unimolecular eliminations, E1 reactions. Alright, so E1 reactions are kind of similar to SN1 reactions in the sense that only one of the two reactants plays a big role in the transition state. And on top of that, the delta S double dagger of the transition state is positive, meaning that the reaction is becoming more disordered at that transition state. So kind of like SN1 reactions, what that really implies is that your substrate is going to have to undergo um, the breaking of the bond to the leaving group. So the leaving group is going to have to take off and it's going to have to form that carbocation intermediate that we saw with SN1 reactions. And in essence, in this first step, an E1 reaction and an SN1 reaction are identical. Now this kind of creates issues, of course, because the fact that the rate determining step is leading to the same intermediate for both reactions means that from here on out, you could actually go either way. So, yeah, the conditions are a little bit more iffy for SN1 and E1s. But pretty much, if your nucleophile behaves as a base as opposed to a nucleophile, you'll end up removing one of the alpha hydrogens uh, with respect to the carbocation. And in doing so, you will form an alkene and of course the conjugate acid of the base. Okay, now pretty much what's going to happen right here is that because the carbocation is the hardest point, really the hardest species to form, and it's really reactive, you have very little room to allow the SN1 to be unique in comparison to the E1 reaction. And at the end of the process, the E1 is always going to be in competition with an SN1. It's almost unavoidable. You can limit the extent by which they're going to be competing, but you will have a little bit of it in there. So to give you an example, we have this secondary alkyl halide. And notice that on the left side we have alpha hydrogens, on the right side we have an alpha hydrogen. And this alpha hydrogen is different from that one because this one is an alpha hydrogen next to two methyls, whereas this alpha hydrogen is next to a methyl and an ethyl. So they are different and they're going to yield different products. But in addition to that, you have to consider the following. Um, the conditions here are basically protic solvent, and technically not a relatively good base, but you are heating the reaction, right? So the heating is actually kind of what's going to let you know that this reaction is probably going to prefer to go via the elimination route. The base is really not a good base, and the big reason for this is that, this is the crab base once again. The reason for this is that you're going to generate a carbocation. You cannot have a strong base present in solution if you have to generate a carbocation. So this is spelling out an E1 mechanism for your reaction. The fact that you're heating the reaction, the fact that you're using a crab base, tells you, yeah, elimination via a unimolecular process. And what that really means is that you're going to remove this chlorine out of the molecule, producing your carbocation. This one is a secondary carbocation. Now, what you may recall from our discussion of SN1 reactions is that if you generate a secondary carbocation, you have to look at the neighboring carbons. Because if the neighboring carbons are tertiary or quaternary, you're undergoing migration. And in this case, the neighboring carbons happen to be tertiary. So you're going to have hydride migrations that will allow you to basically switch over this um, carbocation from the secondary position to the tertiary position on the left side or the tertiary position on the right side. And even though I'm not showing you this here, it's important that you know the mechanism, right? You have a CH bond on this carbon. That entire CH bond is being transferred over, so you will have to show with an arrow that this CH bond is what's coming over here, allowing the formation of the carbocation here on the left side, or if the CH bond here on the right side is what's coming over, then you develop the carbocation on the right side of the molecule. Okay, now each one of these carbocations, although with much higher preference on the tertiary carbocations, each one of them is going to produce a product. And you have to consider each one of the alpha hydrogens. So on the one hand, if you look at the blue carbocation, this carbocation is next to CH3s, which are equivalent. So if you remove the proton from the CH3 and you draw the alkene from that proton towards the carbocation, you have the following alkene product. On the other hand, this carbocation is next to this set of alpha hydrogens. And if you draw a double bond from that alpha hydrogen towards the carbocation, you generate the following product. Likewise, uh, the carbocation, actually the red one right here, if we look at the neighboring hydrogens, we actually have three kinds. We have a CH3, we have a CH2 that is part of an isobutyl group, and we have a CH2 that's part of an ethyl group. So you have three different hydrogens to choose from. And so the hydrogen could come from the methyl group, and if you draw a double bond from that alpha hydrogen set to the carbocation, you end up with this product here. Alternatively, you could start with the hydrogens here on the right side, which are adjacent to the carbocation, and if you draw a double bond starting from those set of hydrogens to the carbocation, you will get a different product. You'll get the product that's right here on the bottom. And of course, if you choose the hydrogens here on the left side and you draw a double bond towards the carbocation, you get the product in the middle. And these are technically the major alkenes that you expect to get, although truth be told, if you also draw the products of the secondary carbocation, you're gonna get products that are already present in this list. You're gonna get this alkene on the very bottom, and you're also gonna get the alkene here in the blue, scheme. So altogether, what I'm trying to show you is that you're gonna form a lot of products out of your E1 elimination reaction. And out of them, the ones that will be the major products are going to be the ones that are the most substituted. So notice that between the two blue outcomes, this one is disubstituted, whereas this one right here is trisubstituted. So the trisubstituted is going to be the major one out of the two. And among these ones, this alkene is disubstituted, whereas this one is trisubstituted, and so is this one that's trisubstituted. So you expect those two also to be major products. So needless to say, this is not a great reaction because you're going to get way too many things. And on top of that, if there is the possibility for the alkene to have the E and C isomers, you're going to have both. Mind you, the trans isomer is going to be more predominant than the cis isomer, but you will still get both. So this is a big mesh of products. And this is kind of the problem with unimolecular reactions. They tend to yield too many things as a result of the fact that you are producing carbocations which can rearrange. And on top of that, you not only have the elimination products, you're going to have a small amount of SN1 products as well. So that's, even though we're not drawing them because they're not going to be the major products, some small amount of it is going to be formed. So these type of reactions, unfortunately, are not the greatest. There's some situations where E1 reactions will lead to a minute amount of products, but in this case, that's not what's going to happen. Okay, so in the next video, I will talk to you about the factors that do favor E2 reactions and E1 reactions. So see you in the next video.